Jai Hind students, welcome to my YouTube channel. Students, there are various secrets to success and you'll be amazed to know that the secret to success lie in your own room. Let me clarify you, or let me try to convince you. Just look at the roof. The roof will suggest to aim high. Look at the fan in your room. It will suggest you to remain cool even during trying circumstances. Students, look at the watch. Look at the clock. It will suggest you that every minute, every second of your life is precious. And students, don't forget to look at the mirror, which I know you often do. It will suggest, reflect before you act. So it will suggest you to introspect your actions. So the success, it lies entirely on your approach and your attitude. So students, with that note, let's begin this session. And in this particular episode, we are going to discuss some additional numericals based on human eye and its defects. Right? So let's start with the first question then. I'll read out the question for you. The near point of a hypermetropic eye is 50 cm. Find f of a focal length of a convex lens actually, used in his spectacles. First, hypermetropic eye. You are aware, hypermetropic eye is also known as farsightedness. In this case, the person is capable of seeing or viewing the distant objects clearly, but is unable to see the nearby objects clearly. And in order to correct the hypermetropic eye, we make use of a convex or converging lens. Right? So let's do this question. Near point of the hypermetropic eye is given to be 50 cm. Right? And you are supposed to find out the focal length of the convex lens, which is to be used in his spectacles. So, for the lens to be used, as spectacles, we are aware of this formula, lens formula, 1 by v minus 1 by u is equal to 1 by f. This focal length of the spectacles is to be found, right? So here u, it is equal to, students, minus d. D is the least distance of distinct vision. And in case it is not given, then it has to be taken as 25. D is always taken to be 25 cm. And V, it will be the near point of this person who is suffering from hypermetropia. It is given to be 50 cm. We have already done the theoretical portion. During the discussion of the correction of the eye defects, we have discussed it in detail, right? So, here u would be equal to minus d, v would be equal to minus 50 cm. Right? So, in the case of hypermetropic eye, the near point increases from 25 cm. It is more than that of 25 cm. So, let's substitute this value over here. So, what do you get? 1 by v, that is minus 50, minus 1 by u, it is minus d, and it is 1 by f. D is, we'll take D as 25 centimeter, no doubt regarding this. So, it is minus 1 by 50 plus, minus 1 is plus 1 by 25 is equal to F. Right, students? So, we can easily get the value of F. It is equal to, 50 can be taken as LCM. So, it will be equal to minus 1 plus 2. So, 1 by 50, or f is equal to 50 centimeter. So the focal length of the convex lens to be used by that person suffering from hypermetropia should be 50 centimeter. It could have been done by using the formula directly. We have discussed this formula, students. In fact, we have derived this formula. In the case of a person suffering from hypermetropia, the focal length of the specs to be used is given by xdv. divided by x minus d. This is the formula. Clear? In any numerical concerning hypermetropia, this formula can be used. X is the near point. X is the near point of the hypermetropic eye, which must be greater than 25 centimeter. D is to be taken as 25. So directly substitute the value and you will get the answer. Look, X is the near point of the hypermetropic eye, which is 50. D is 25 divided by 50 minus 25. Isn't it? So it will be 50 into 25 divided by 25. So it will be equal to 50 centimeter. So students, it's up to you. Either do it by conventional method or you can use this formula directly. In case you have got any doubt, then you can refer to the previous videos, the link of which I will be giving in the description section of this episode. Right? So this is the formula which you can use directly in case of numerical concerning hypermetropia, that is farsightedness. X is the near point of the hypermetropic eye. D, it is to be taken as 25 centimeter. And F is the focal length of the lens to be used. It will come out to be positive, which means that the nature of the lens must be converging. That is, convex lens is used to treat hypermetropic eye. Right? Okay students, let's consider the second question. Second question is, the far point of a myopic person is given to be 120 centimeter, and we are supposed to find out the focal length of the lens which will be required to enable him to see the distant objects clearly. So the previous question was based on hypermetropia. This question is based on myopia. So let us deal with it. First we'll do it by conventional method and then we can make use of the formula directly, right? So, second one. Far point. Now in the case of a myopic person, he is able to see the nearby objects clearly, but is unable to see clearly the objects beyond a certain distance. So far point of a normal eye is infinity. But for a person suffering from myopia, the far point decreases from infinity. It decreases, it deteriorates from infinity. Clear? So here the far point of the myopic person is given to be 120 and we are supposed to find out F. So again the lens to be used, for the lens which is to be used by him as spec, it will be 1 by V minus 1 by U is equal to 1 by F. Here students, U it will be equal to minus infinity. The myopic person, the normal far point of a normal eye is infinity, that is to be taken as U. In the previous case, the near point of a normal eye, that is 25 centimeter, that is capital D, it is to be taken as U in the previous question. Here U is to be taken as infinity, the far point of a normal eye. Right? And V, it is to be taken as the far point of the myopic eye, which is 120 centimeter. Obviously with negative sign. It will be virtual. It will be on the same side as that of the object. Right? So if you substitute the value over here, what you get is minus 1 over minus infinity is equal to F. 1 by infinity is 0. So we get 1 by F is equal to 1 by minus 120. So F is equal to minus 120 centimeter. This negative sign suggests that the nature of the lens is diverging. That is, we are talking about concave lens. So, in order to rectify the myopic eye, concave lens of suitable focal length or power is to be used. Right? So, in case of numericals concerning myopia, the formula to be used is F is equal to minus X. X is the far point of the myopic eye. So, this is the formula which you can use directly. X is the far point of the myopic eye. which would obviously be less than infinity, right? So directly you can write f equals to minus 120. It could have been achieved directly by using this formula. Again, I must remind students, in case of any doubts in the concepts, go back to my previous videos, the link of which I will give in the description section of this present video. Clear? So do watch those previous videos as well to completely understand. Okay, let's proceed with the third question now. For a normal eye, the near point is given to be 20 centimeter. Instead of 25, it is given to be 20 centimeter. From the eye lens. Here we are not talking about any spec, any external lens. We are talking about eye lens. This is suppose the eye lens. As you are aware, our eye lens is more convex at the back than at the front. And this is suppose the retina. Image is formed at the retina. This is retina. And let us consider this to be our eye lens. Okay. Now the question is, the near point is 20 centimeters. So here the object is placed, it is placed at 20 centimeters. So this is given to be 20 centimeters from the eye lens. The distance between the eye lens and the retina of the eye is 2 centimeters. So the image is formed at 2 centimeters, which is the distance between the retina and the eye lens. This is U and this is V. We are supposed to find out the power of the eye lens. First we will determine the focal length and then we can easily get the power of the eye lens, right? So for lens, this is the formula. 1 by V minus 1 by U is equal to 1 by F. Here students, U is, make use of sign convention, incident ray is traveling along this direction, so we are measuring along this direction, so it will be minus 20. V would be, it is real and inverted, so along the same direction as that of the incident ray, so it will be plus 2 centimeters. So let's substitute the value over here. So 1 by V, 1 by 2 minus 1 by U is minus 20. So let's solve it. 1 by 2 plus 1 by 20. So 20 would be the LCM, 10 plus 1. So it is 11 by 20. Therefore focal length is 20 by 11 centimeter. Clear students? But in this question we are supposed to find out the power of the eye lens. Now power of the eye lens is 1 by F in meters, or this is in centimeters, so it will be 100 by F in centimeter. So mathematically we are aware the power of a lens is given by the reciprocal of focal length in meters. In case it is in centimeters, so it will be 100 divided by F. So let's substitute the value. 100 divided by F. F is 20 by 11. 20 by 11. So we get 55 diameter and with positive sign. So the nature of the lens is converging or convex. It is very much the fact that our eye lens is of converging nature. So this is how you need to do such questions, right? This is a very, very good question indeed. Let's proceed further. Let's concentrate on the fourth question then. Okay, fourth question, students. Again, it's the case of a normal eye. For a normal eye here, instead of near point, as was in the case of previous question, the far point is given. The far point is at infinity from the eye lens, right? The image is formed at the retina, which is 3 centimeters away from the eye lens. What is the power of the lens? We are supposed to find out the power of the lens. So we'll proceed exactly the same manner as we have done for the previous question. Okay. Now this is the eye lens, suppose. And let us consider this to be the retina of the eye. This is where it acts as a screen. So at the retina, the inverted image is formed, right? And for a normal eye, image is formed exactly on the retina. So, this is suppose the principal axis. The far point is at infinity. Okay, U is infinity. And the image is formed at the retina, which is 3 centimeter away from the eyelids. Okay, this is given to be 3 centimeter. This is where the object is formed, so it is V. It is plus 3 centimeter. We are supposed to find out the power. First we will find out the focal length, and then we can easily find out the power of the eye lens under consideration. Right? So for the eye lens, make use of lens equation, which is 1 by V minus 1 by U is equal to 1 by F. So 1 by V is plus 3. U is minus infinity. F is to be found. So 1 by F is equal to 1 by 3. That is, F is equal to 3 centimeter. Right? So focal length of this eye under consideration is 3 centimeter. So what about the power then? It is reciprocal of focal length in meters. Here we have calculated the focal length in centimeters. So for that it will be 100 by F in centimeters. Clear? So what you get is 100 divided by 3. And SI unit of power is diopter or meter inverse. So power would be 33.33 diopter. Again with positive sign, which suggests that the eye lens is of converging nature. It is convex lens or converging nature. So this is the solution of this particular question. Right? Very, very simple indeed. Okay, let's proceed to the next question then. In the last two questions, we can make use of the formulas directly, right? So question number 5. A person suffering from farsightedness. Farsightedness means hypermetropia. Wears a spectacles having a convex lens of focal length 40 centimeter. What is the distance of near point of his eye? Near point of a normal eye is 25 centimeter. As I have told you, if a person is suffering from hypermetropia, right, or farsightedness or long-sightedness, then his near point increases. It must be greater than 25. So without doing any sort of calculation, you can easily predict that the distance of the near point of his eye must be greater than 25 centimeter. Clear? And in case of a myopic eye, the far point gets deteriorated. For a normal eye it is infinity, but for a myopic eye it will get reduced from infinity to some finite value. It will be less than infinity. So, question number 5. Let me read out the question once again. A person suffering from farsightedness. Farsightedness means hypermetropia, where a person is able to see clearly the distant objects but is unable to see clearly and distantly the nearby objects. So in case of hypermetropia or farsightedness, the near point increases. It is greater than that of 25 centimeter. So convex lens is to be definitely used so as to rectify hypermetropia or farsightedness. So a person suffering from farsightedness wears a spectacles having a convex lens of focal length 40 centimeter. So he is using a convex lens. Its focal length is positive. So it is plus 40 centimeter. Fine. What is the distance of the near point of his eye? Now D, we are aware it is 25 centimeter. And X is to be found. What is X? It is the near point of the hypermetropic eye. Clear? Or farsightedness. Person suffering from farsightedness. The near point of the eye of the person suffering from farsightedness. What is the formula, students? In the first two questions, we have discussed the formula to be used. In case of hypermetropia or farsightedness, the formula to be used is F is equal to XD divided by X minus D. This is the formula to be used. And in case of myopic eye, the formula to be used is F equals to minus X. D is the distance least distance of distant vision, which until and unless otherwise given in the quotient, it should be taken as plus 25, right? While x in this case is the near point, while in the case of myopic eye, where we make use of the formula f equals to minus x, there x would be the far point. But anyway, coming back to this quotient, this formula can be directly used. Just now we have convinced how this formula came, right? By using the same length equation. Anyway, let's substitute the value. What is there? It's given to be 40 plus 40. X, this is to be found. D, which is to be taken as 25. X minus 25. Let's solve it. 40 into x minus 25 is equal to 25x. So that will give us 40x minus 1000 is equal to 25x, which in turn will give us 40x minus 25x is equal to 1000, which further implies that 15x is equal to 1000, or x would be equal to 1000 divided by 15, right? So it will be 200 divided by 3, so it will be 66.67 centimeters. So this must be the distance of near point of his eye. As I told you very early in the question, that near point of the hypermetropic eye must be greater than 25 centimeters. So that is what we have obtained over here. Clear, students? So we are done with question number 5 as well. Now let's proceed to the last question. Last question is, students, a person with a myopic eye. Previous question was the case of farsightedness, long-sightedness or hypermetropic eye. Now the last question is again based on myopia or short-sightedness or nearsightedness. So a person with a myopic eye cannot see objects beyond a distance of 1.5 meter. Look, the far point of a normalized infinity. But this person who is suffering from myopia, his far point gets reduced from infinity to 1.5 meter, right? So what would be the power of the corrective lens used to restore proper vision for myopic eye? The formula to be used is f is equal to minus x, where x is the far point of the myopic eye, which in this case is given to be 1.5 meter. So therefore f is equal to minus, the value of x is given to be 1.5 meter. This is the far point of the myopic eye. So it is 1.5 meter. Clear, students? It's already in meter. So we need to find out the power of the corrective lens to be used. It is 1 by f in meters. So what do we get? 1 divided by minus 1.5. So that will give us minus 10 by 15. So it is minus 2 by 3. Or power of the corrective lens to be used by that person must be minus 0.67 diopter. Diopter is the SI unit of power. Or it can be written as meter inverse. So, negative sign, it suggests that the nature of the corrective lens to be used must be diverging or concave. So, this negative sign suggests that the lens to be used must be a concave lens or it must be of diverging nature. Clear, students? So, by using a concave or diverging lens of power 0.67 diopter, the person can rectify his myopic eye. So students, I hope these questions will help you in understanding the concepts involved in the correction of human eye defects. Right? So that's it for this particular session. Do join me in my next lecture. Thank you. And always stay blessed.